Hello and welcome to another tutorial. In this video I'm going to continue the discussion on Newton's method, and so in the previous lecture on Newton's method we discussed how to implement Newton's method in Java based on the recursion that starts with an initial guess. No root bracketings is needed, and that's a plus. That's definitely a plus for Newton's method, because there are two advantages of Newton's method when you compare it to bisection, secant, or Brent's method. The first one is that it doesn't need a bracket for the root. You just have to start with an initial guess. Obviously, the downside is that the roots should be close enough. Otherwise, the Newton's method may not converge. But the other thing is that Newton's method has a quadratic convergence rate, which is better than bisection, which is linear, or secant and Brent, which is super linear. Like the convergence rate is 1.4, 1.5, around that number, not exactly 2. But for Brent, things are a little bit different, because for Brent you can use different interpolating functions. If you recall, in the Brent we used a quadratic function for interpolating. Now some implementation of Brent's method may use a hyperbolic function to do the interpolation. You don't need to just use a quadratic polynomial. Quadratic function to x, quadratic, let's rather say quadratic polynomial. Okay, but the advantage of Newton's method, you just need to have one root. If you recall, we said that there is no need for bracketing, but if you want to find all the roots, you can divide it into sub-intervals, and the roots may in fact fall into some of the sub-intervals, so they are already bracketed. And then we apply the Newton's method in each bracket or in each sub-interval, and then we have to figure out a good convergence condition for the Newton's method in each sub-interval. Okay, and as I mentioned, even if fa times fb is positive, which means the interval of a and b may not be a valid bracket for the root, and that causes the bisection, trisection, or the secant method to potentially fail, Newton's method may very well converge the root, right? Let's head to Eclipse and look at the Newton's method that we wrote in the previous lecture. And in that in that lecture we said that we should have a stop criteria for the iterations. So initially we pass the maximum number of iterations, and in each recursion we reduce that number by 1 unit, and when it hits 0 we quit, we give up and say that okay, max iterations reached and we couldn't find the root, so the root, we just return a nan, not a number, right? But then we also said that if the root is in fact found, the stop criteria or the convergence criteria would be the value of the function is less than the absolute error. Unfortunately, this is not a good convergence criteria. So what I've done here is that I changed it, I put it here. So after the initial guess, at this step, we calculate the x, the next step, the value for the next step. And then we calculate the relative errors and also the absolute error based on the guess. Or we could have based on the x2, based on the new value or the previous value. Doesn't really matter. But then the key here is that I'm also including the relative errors. So relative error number 1 is x2 minus guess divided by guess. Relative error 2 is x2 minus guess divided by x2. And the reason that I'm using both, because one of these, guess or x2, might be 0. There's a very high chance that we set the initial guess to 0. So if I just use this, division by 0 returns infinity, which is not a good convergence criteria. Okay, So we compared two relative errors to the relative error that we said initially for the convergence, and also the absolute error for the absolute error convergence. And if one of these satisfies, then we return guess. And to recap, the absolute error and the relative errors, I've set them to 1e negative 15. Typically, the relative error is reached first, then the absolute error, but sometimes the absolute error may reach first. Okay. Now, if you recall, we tried to do we tried to search for all the roots of x times sine of x in the interval of -5 to 10 with 100 subintervals and 1000 max iterations for each subinterval, and we couldn't find all the roots. But now with this new convergence change, with this new convergence criteria, if we run the code, we see that we can find all the 5 roots: 1, 2, 3, 4, 5 roots. 0 minus pi, 3 pi, pi, and 2 pi. And it doesn't care if one of the roots is a tangent root. It doesn't really care, as long as the function is smooth and nicely behaved, has all the derivatives, then the Newton's method is guaranteed to give us very fast convergence. Now let's say I start with an initial guess of now here we were looking for all the roots, but let's try to find one root, which is test number 1. Function is x times sine of x, and I want to find the root with the start guess of max dot pi. We know that this function at pi has a 0, right? It immediately gives it, but there is a point that the derivative is 0, and it's about 2.03. so let's start with that. So let's start with a point that the derivative is almost 0. Let's see what happens. It returns 571, so it definitely doesn't return a good value, and that's because if it was exactly 0, then we can't find. The Newton's method completely fails. So we can call this a failure of the Newton's method, because 571 is not a valid root near 2. Okay? Alright, let's put this 1.9 minus pi. So if I set to 1.9 is here. So it draws a tangent, it goes here, so 1.9 here, and then it tries to converge to the root. So it could either converge to 0, minus pi, or 0, and we see that it actually converges to I assume if we draw the tangent line at 1.9, it hits somewhere around here, then we get negative slope. And so if we try to get to a point that gives us 0, maybe let's try 1.4 for example. Now it returns 0, it converges to 0. Okay, so this is a much better convergence criteria for Newton's method, and it's pretty fast. Let's head to the PowerPoint. So the failures of Newton's method: one of them is obviously bad starting point. If the derivative is 0 right at the beginning, we cannot move forward, right? So the Newton's method fails. Or the derivative is not defined at the beginning. So I have a function, for example, but the function doesn't have a derivative. The derivative doesn't exist at the beginning. So we might very well be stuck right at the beginning because of the fact that the function doesn't have a derivative. But if the function is a smooth function, well behaved, we definitely have a very fast convergence. Okay, so if the function is not smooth, then we might run into some points, not only in the beginning, maybe at some point during the recursion we might run into a point that the derivative doesn't exist. It doesn't have to be in the beginning, but it might be at some point during the iteration. So that could also make the Newton's method fail. But there's one more thing that we discussed before, is that if I know the analytic value or analytic expression for the derivative function, we should be able to set it analytically instead of numerically calculating the derivative. So let's head to Eclipse. I'm going to create a new interface and call it a real root deriv function. And just like before, I'm going to annotate it with functional interface. Alright, for the compiler to double check that it's a functional interface. And I'm going to have a method double values at some point x. Alright, now this returns an array of doubles, and what I'm going to consider here is that basically value 0 is going to be f of x, values 1 is going to be f prime of x, and values 2 is going to be f double prime of x, and etc. Okay, so at the moment I don't know the length of the return, and the length is determined when I actually implement this interface. If we compare it with the real root function, we had a method called value, and it only returned the value of the function f of x, returns f of x. But now I can return the higher order derivatives also. If I have this, I can go back to the real root class and define also a real root deriv function, from the and call it deriv func. Okay, and then I can overload the constructor. So if I pass the real root function, I use the real root function and then make the deriv function null, which is by default is null. But then I can have another overloaded constructor and pass the real root deriv function, deriv func. And then what I'm going to do is that I set the deriv func and set the func to null. So this way I can check which one has been set by the user. So if user passing the deriv function, I'm going to assume that the user has already analytically written down both the function and the expression for the deriv. Now in the Newton's method, what I'm going to do is when I'm here, I try to, so we only need to find the value of the coef. Okay, so double coef is basically, let's say 0 right at the beginning. Actually we don't need that, so let's check for deriv function. If deriv func is null, we're going to do this. We're going to find the derivative and then do the recursion. Else if basically func equals null, so one of them has to be null. And then what we're going to do, we don't need to find the basically the derivative numerically. So what I'm going to do, I'm going to just call the deriv func, and basically what I'm going to do here, so the func is null, so x1 is guess, we're going to get call the derifunc and values at x1 or at guess, and then this is going to return a double. Let's call this values or vals. Okay, and then y1 is vals double y1 equals vals the 0th element, and double coef is vals the first element. All right, and the stuff is the same, so no need to numerically calculate the derivative. So let's go to the test Newton class. We're running test 1. Let's make sure the previous implementation works. Yes, still returns 0. And let's create a third test, test 3. And we're going to run test 3. This time I'm going to, instead of real root function, I'm going to implement the real root deriv function. Derifunc equals new, or maybe I can just say x goes to a new double array, x times math dot sine of x as the first element, which is the function, and the derivative is math dot sine of x plus x times math dot cosine of x. All right, and then we're going to run or maybe let's just call it func. And then here we're going to call the values and then get the first element, so everything should be fine here. Null pointer exception. Oh, okay, so we're going to use the derifunc here, call the values, and then the first. Actually, we don't need that. It's just y1, right? So we didn't need to actually call the function again. We can just use the y1 value because y1 was the value of the function. Maybe let's just make it in a explicit way. Okay, y1 is the value of the function, I guess. All right, let's run this. Yes, it returns 0. And let's try the other version that returns all the roots. A list of double roots is root finder dot Newton so -5 to 10 sub intervals, 1000 iterations per sub interval, and let's call it also root. We don't need to make it plural. Yes, it can find all the roots. So 0, -pi, 3pi, pi, and 2pi. As you can see here, I'm passing it the function f and f prime. So maybe let's just write it here as a comment. Analytically defining f of x and f prime of x. So sometimes this is a better option than using the trying to numerically estimate the derivative. Okay, so we can use either of these, and for the previous cases, for the previous methods like the Brent method or the secant or the bisection, we really didn't need to have any need. We didn't have any needs for the first derivative or the second derivative. But for Newton's method and the next method, which is a generalized Taylor method, we do need to calculate the higher order derivatives. So if we have them analytically available, if we have an analytic expression, then we can just use the real root deriv function. If we don't know them, we can use the real root function and then numerically calculate them. Okay, thank you for watching, and I'll see you in the next video.